All right, let's get into it. Number 10. The universe is expanding too fast. There are two ways to measure how fast the universe is stretching apart. Both methods are precise. Both have been refined across decades by Nobel laureates using the most sensitive instruments ever built. And they don't agree. Not by a little. By enough that in January 2025, Duke University physicist Dan Skolnick looked at the latest data, published his results in the Astrophysical Journal letters, and said in plain language, the tension now turns into a crisis. Here's the setup. Method 1 uses the oldest light in existence. The cosmic microwave background, the faint afterglow of the Big Bang, was mapped in staggering detail by the European Space Agency's Planck satellite. When cosmologists plug that data into our best model of the universe, on a framework called lambda CDM, they get a clear answer. The universe should be expanding at 67.4 kilometers per second per megaparsec. That number is clean. It is confident. It has very tight error bars. Method 2 measures the universe as it exists right now. Teams led by Nobel laureate Adam Rice at Johns Hopkins University use Cepheid variable stars, pulsating stellar lighthouses whose brightness is predictable, to calculate distances to galaxies. They measure how fast those galaxies are racing away from us. And the answer comes back: 73 kilometers per second per megaparsec. 67 versus 73. That is an 8 to 9% discrepancy. In cosmology, that is not noise. That is a 5 sigma statistical divergence. The gold standard in physics for this is real and it is not going away. For years, skeptics hoped the problem was measurement error. Maybe the Hubble Space Telescope was blurring the Cepheid data. Maybe interstellar dust was corrupting the calibration. So in 2024, Reese and his team pointed the James Webb Space Telescope, the most powerful observatory ever placed in orbit, at the exact same stars. Webb sees in infrared. It cuts through cosmic dust like it doesn't exist. Its resolution makes Hubble look like a disposable camera. The result confirmed every previous measurement. The data wasn't wrong. The universe really is expanding faster than our best model says it should. And then the DESI collaboration. The Dark Energy Spectroscopic Instrument mapping over 15 million galaxies from the Kitt Peak Observatory in Arizona. Released data in 2024 and 2025 suggesting that dark energy, the mysterious force driving the expansion, may not be a constant at all. It might be evolving, changing its strength over cosmic time, which means the fundamental force stretching the fabric of reality might itself be unstable. Think of it this way: you are building a bridge. You measure it from the left side, 200 feet. You measure it from the right side, 217 feet. You check your instruments, perfect calibration. You measure again, same numbers. The bridge has not moved. Your tools have not failed. The math is flawless from both ends, but the bridge cannot be two lengths at the same time, which means your understanding of what a bridge is, the basic rules of geometry you have relied on your entire career, and is wrong. Not the tape measure, the rules themselves. The lambda CDM model is the backbone of everything we think we know about the cosmos. It tells us how galaxies form, how matter clumps, how old the universe is. If lambda CDM is wrong, it is not like getting one question wrong on a test. It is like discovering the textbook was written in a language that nobody actually speaks. And with every new telescope, every new data set, every refinement of measurement, the gap between what we predicted and what we observe does not close. It widens. The better we measure the universe, the less it makes sense. Number 9, the galaxies that shouldn't exist. It is 2022. You are sitting in a dark control room at the Space Telescope Science Institute in Baltimore, Maryland. The James Webb Space Telescope, 25 years and $10 billion in the making, has just sent back its first deep field images of the early universe. You expected to see infant galaxies, small, faint, still assembling themselves from primordial gas. Instead, you are staring at massive, fully formed galaxies that look like they have been around for billions of years. Except, according to the timestamp of their light, they existed when the universe was less than 700 million years old. They should not be there. They cannot be there. But they are. The team gave them a name: Universe breakers. The standard cosmological model predicts galaxy formation as a slow, deliberate process. Dark matter collapses into enormous halos. Ordinary matter falls into those halos over hundreds of millions of years. Stars ignite, and galaxies assemble. It takes time, an enormous amount of time. But JWST found galaxies up to 100 times more massive than our models permit for that era. Joel Leja, an astrophysicist at Penn State who co-authored the discovery paper, put it bluntly. The revelation that massive galaxy formation began extremely early in the history of the universe upends what many of us had thought was settled science. We have been informally calling these objects universe breakers, and they have been living up to their name. Then, through 2024, JWST surveys identified a completely new class of object, the little red dots. Over 341 of these peculiar, compact, deeply red galaxies from the earliest epochs of the cosmos have now been cataloged. The many appear to harbor supermassive black holes gorging on surrounding matter so violently that they outshine entire galaxies. The Sears team at the University of Texas confirmed in August 2024 that accounting for these active black holes was critical to understanding why early galaxies appeared so impossibly bright. And in early 2025, JWST revealed a galaxy nicknamed the Big Wheel, a massive spiral structure as organized and elegant as our own Milky Way, existing within the first 2 billion years of the universe. Spiral galaxies require gravitational stability. They require time. They require peace. The early universe was supposed to be a violent, chaotic mess. Finding a calm, beautiful spiral that early is like finding a cathedral in the middle of a forest fire. Erica Nelson, on the University of Colorado astrophysicist who first identified the universe breakers, said something that should echo in every physicist's nightmares. If even one, especially one of the really massive ones, is there, it is a problem. Not a curiosity, not an anomaly worth a footnote. A problem. For the entire framework we use to understand reality, we built JWST to photograph the birth of the cosmos. Instead, it is showing us that the infant universe looked nothing like our equations said it should. And every month, it sends back images that make the gap between prediction and reality a little wider, a little more undeniable, and a little more unsettling. Number 8. 95% of the universe is missing. Look at your hands. Look at the screen in front of you. Look out the window at the trees, the sky, the sun. Everything you have ever seen, touched, measured, or loved, all of it, every atom of visible matter in the entire observable universe, makes up less than 5% of what is actually out there. The other 95% is invisible, undetectable. And after decades of searching with every instrument we have ever constructed, we still cannot tell you what it is. We are a rounding error in our own universe. The Planck satellite's measurements, combined with the lambda CDM model, break it down like this. 68% of the universe is dark energy, 27% is dark matter, and 5% is ordinary matter. The protons, neutrons, and electrons that build every star, every planet, every living thing. Dark matter acts like an invisible skeleton holding galaxies together. We can see its gravitational fingerprint on the rotation curves of galaxies, on the bending of light around massive clusters, on the large-scale scaffolding of the cosmic web. It shapes everything we observe, and we have never directly detected a single particle of it. The LX Zeppelin detector, the most sensitive dark matter experiment on Earth, buried 4,850 feet underground in a former gold mine in South Dakota, reported in 2024 that it found no evidence of WIMPs, the weakly interacting massive particles that had been the leading candidate for dark matter for over 3 decades. We are running out of places to look. Dark energy is stranger still. It is the name we have given to the force accelerating the expansion of the universe. And it was discovered in 1998 by 2 independent teams studying distant Type 1a supernovae, a discovery that won the 2011 Nobel Prize in Physics. But calling it dark energy is generous. It is a placeholder, a label pasted over a profound ignorance. And now, with DESI's 2024 and 2025, Data suggesting dark energy's density may be evolving over time. Even the placeholder might be wrong. Imagine living in a house. You can see the furniture, you can walk on the floors, you can turn on the lights. But the walls are invisible. The foundation is invisible. The structural beams, the plumbing, the wiring, invisible. You know they exist because the house is standing. But in 100 years of searching with every tool available, you have never found what the house is actually built from. Now imagine being told the invisible walls might be shifting. Oh, the foundation might be weakening, and you have absolutely no way to verify it because you still cannot detect the material you are standing on. That is not a metaphor. That is a literal description of the universe you inhabit. Number 7. The star that is older than the universe. The universe is 13.8 billion years old. The Planck satellite confirmed this. The cosmic microwave background confirms this. Every reliable measurement converges on the same number, 13.8 billion years. It is one of the most precisely known values in all of cosmology. And then there is HD 140283, a star sitting 190 light-years from Earth. In 2013, a team led by Howard Bond at Penn State University used the Hubble Space Telescope to pin down its distance using parallax measurements, and then combined that data with established models of stellar evolution to calculate its age. The best estimate came back, 14.46 billion years, plus or minus 800 million years. That central value is 660 million years older than the universe itself. The error bar technically allows the star to be younger than the cosmos. Barely. At the extreme lower end of the uncertainty range, HD 140283 could be about 13.66 billion years old, which would make it almost exactly as ancient as the Big Bang. But the central, most probable value stubbornly insists on being older, and HD 140283 is not alone. The Milky Way's halo harbors a population of ancient stars, known as population 2 stars, whose estimated ages all cluster uncomfortably close to the age of the universe itself. It is not one inconvenient data point. It is a pattern, and a whisper from the oldest objects we can find quietly insisting that our timeline might be wrong. Think of finding a tree in a forest that is older than the soil it is growing in, not a little older. Hundreds of millions of years older. You can count the rings. You can date the dirt. Both measurements are solid, and they flatly contradict each other. Either the tree is wrong about its age or the ground is wrong about when it was made. Either way, something fundamental about how we date reality is broken. The Methuselah star does not explode. It does not emit strange signals. It does not do anything dramatic. It simply burns 190 light-years away, being impossibly old. And every time we refine our models, it does not get younger. It stays right where it is, stubbornly, defiantly ancient. I'm whispering something the rest of cosmology does not want to hear. Your timeline is wrong, and you have no idea by how much. Number 6. The 330 million light-year hole in space. In 1981, astronomer Robert Kirshner and his colleagues at the University of Michigan were conducting a redshift survey when they stumbled onto something that should not exist. A void. Not a small gap in the cosmic web, not a quiet neighborhood between galaxy clusters. A void 330 million light-years across, containing roughly 60 galaxies in a volume where there should be 2,000. They called it the Boötes void. And to this day, no one can fully explain it. To grasp the scale, the Milky Way is about 100,000 light-years in diameter. You could line up over 3,000 Milky Way galaxies across the Boötes void and still not span its width. And inside that staggering volume of space, almost nothing. A cosmic ghost town on a scale that makes the word empty feel inadequate. The standard model of cosmology predicts that matter should be distributed fairly evenly on the largest scales. A foamy, web-like structure with galaxies clustered along filaments and voids in between. Small voids are normal, expected, but the Boötes void is too big, too empty, too clean. Some astrophysicists have proposed it is actually a merger of smaller voids that gradually connected over billions of years. But even that explanation requires the voids to have formed and linked in a way that pushes the boundaries of what lambda CDM comfortably allows. Here is the thought experiment that makes this personal. If the Milky Way were located at the center of the Botas void instead of where it sits now, we would not have discovered the existence of other galaxies until the 1960s. For almost the entire history of human civilization, we would have looked up at the night sky and seen nothing beyond our own stars. We would have believed with absolute certainty that we were alone, not just alone on Earth, alone in the universe. The sky would have been dark, empty, and silent, and we would have had no reason to suspect otherwise. The Botas void is a reminder that the universe is not obligated to put things where we expect them, and it raises a question we cannot answer. How do we know we are not inside a void right now? A void so vast that what we call the observable universe is just a small, populated island in an ocean of emptiness we have not yet detected? We assume we sit in a representative patch of cosmos, but the Botas void proves the cosmos does not distribute itself fairly. Some regions are rich, some regions are deserts, and we have no way of knowing which one we are in. Number 5. The star that blinks like something is feeding on it in 2015. Astronomer Tabitha Boyajian at Yale University noticed something wrong with a star designated KIC 8462852. The Kepler Space Telescope had been monitoring it for 4 years as part of its planet-hunting mission, and the data showed a pattern that had never been observed in any other star in the survey. Periodic, irregular dips in brightness of up to 22%. For context, when Jupiter, the largest planet in our solar system, transits in front of a star, it blocks roughly 1% of the light. And whatever was dimming Tabby's star was blocking 22 times more light than the biggest planet we know. And the dips were not regular. They did not repeat on any clean orbital cycle. They varied wildly in depth and duration. Some lasted hours, some lasted days. No two looked alike. The most exotic hypothesis captured the world's attention almost immediately: an alien megastructure, a partially constructed Dyson swarm, a constellation of solar collectors built by an advanced civilization to harvest the star's energy. The physics of such a structure would produce exactly this kind of irregular, deep, periodic dimming. It was speculative, it was extraordinary, and no one could rule it out. Subsequent multi-wavelength observations tilted the balance slightly toward a natural explanation. Now, the dimming appears to be somewhat stronger at shorter wavelengths, suggesting fine dust particles rather than solid structures. But dust does not explain the long-term secular dimming. Historical photographic plate data shows that Tabby's star has been getting fainter by about 14% over the last century. Dust clouds do not persist and intensify on that timescale. No single natural model simultaneously accounts for all observed behaviors. The leading explanations, cometary debris, exocometary swarms, intrinsic stellar variability, circumstellar dust, each explain part of the data. None explain all of it. Something is happening at KIC 8462852 that we have never seen before. After a decade of observation with the most powerful instruments available, both on the ground and in orbit, we cannot fully explain it. And the alien megastructure hypothesis, while considered unlikely by the consensus, has never been formally falsified. If, against all expectations, the explanation turns out to be technological rather than natural, the implications are civilizationally shattering. A Dyson swarm does not get built by a species 100 years ahead of us. It gets built by a species millions of years ahead, a species that harvests entire stars for energy. And they are only 1,470 light-years away. In cosmic terms, that is the next room. Number 4. Something outside the universe is pulling us. The Milky Way is moving, not simply drifting along with the general expansion of the cosmos, moving with purpose, being pulled. At over 600 kilometers per second, our entire galaxy, along with thousands of other galaxies in our local supercluster, is racing toward a region of space we cannot see, driven by a gravitational force we cannot identify. In the 1970s, astronomers discovered the Great Attractor, an immense concentration of mass located roughly 150 to 250 million light-years away in the direction of the Centaurus and Norma constellations. Its gravitational pull is equivalent to that of 1,000,000,000,000 suns. That alone was unsettling enough. But in 2008, NASA scientist Alexander Kashlinsky and his team analyzed data from the Wilkinson Microwave Anisotropy Probe and detected something far more disturbing: a large-scale, coherent motion of galaxy clusters streaming in the same direction. Well beyond the range of the Great Attractor's influence, they called it dark flow. Dark flow remains scientifically controversial, because some independent teams have failed to reproduce the signal. Others have confirmed it with separate data sets. But if it is real, the implication is extraordinary. Something beyond the boundary of our observable universe, something whose light has not had 13.8 billion years to reach us, something we can never see, is exerting a gravitational pull on the matter inside our observable universe. This would violate one of cosmology's foundational assumptions, the cosmological principle, which states that the universe is roughly uniform in all directions on the largest scales. If something beyond the horizon is pulling us, there is a preferred direction, an asymmetry, a bias built into the structure of reality itself. Imagine standing in a field. You feel a wind pushing you east, but when you look east, the horizon is flat and featureless. No mountains, no structures, nothing visible generating that force. And then you realize the wind is not coming from anything on this side of the horizon. It is coming from something beyond it, something so far away you will never reach it, no matter how long you walk or how fast you travel. But it is pulling you toward it, right now, at 600 kilometers per second, and it will never stop. If dark flow is real, then the observable universe, the entire 93 billion light-year sphere we have spent decades mapping, is not the whole story. There is something out there, beyond the farthest edge of everything we can see, massive enough to reach across the boundary of observability and tug on the fabric of space. We will never photograph it, we will never name it, we will never understand it. We will only ever feel its pull, dragging us through the cosmos toward a destination we cannot identify, on a trajectory we cannot alter, at a speed we cannot control. Number 3. The silence is not empty, it is afraid. In 1950, physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory. The conversation drifted to the stars, to the billions of potentially habitable worlds, to the near mathematical certainty that intelligent life must exist elsewhere. Fermi listened quietly. Then he asked a question that has haunted astrophysics for 75 years. Where is everybody? The numbers are brutal. The Milky Way contains roughly 200 billion stars. NASA's Kepler and TESS missions have confirmed over 5,700 exoplanets as of 2025, with estimates suggesting there may be more planets than stars in the galaxy, potentially over 1 trillion. Even conservative inputs into the Drake equation, first proposed by Frank Drake in 1961, suggest the galaxy should harbor thousands of civilizations capable of interstellar communication. The Milky Way is 13.6 billion years old. Even at sublight speeds, a single civilization could colonize every star system in the galaxy within a few million years. A cosmic blink. And yet, silence. SETI has listened since 1960. Breakthrough. Listen, the most comprehensive search for extraterrestrial intelligence ever conducted has surveyed over 1,700 nearby stars and 100 nearby galaxies. Nothing. Two solutions are particularly terrifying. The first is the Great Filter, the hypothesis that some catastrophic barrier, either behind us or ahead of us, prevents civilizations from reaching the stars. If the filter is behind us, and we are extraordinarily lucky survivors. If it is ahead of us, we are walking toward an extinction event that no civilization has ever escaped. We have no way of knowing which. The second is the dark forest hypothesis, popularized by Liu Cixin and grounded in game theory. In a universe where interstellar communication takes years or centuries, and you can never verify another civilization's intentions, the only rational survival strategy is silence. Any civilization that reveals its position becomes a target. Not out of malice, out of mathematics. Advanced species do not negotiate. They launch relativistic kill vehicles at any coordinate that emits a signal, erasing potential threats before they mature. The galaxy is silent because every surviving civilization has learned that broadcasting is suicide. And humanity has spent over a century pumping radio signals into the void. In 1974, we deliberately transmitted the Arecibo message toward the star cluster Messier 13, 25,000 light-years away. In 1977, we launched Voyager carrying a golden record with a pulsar map pinpointing the exact location of our solar system. We lit a bonfire in the dark forest, and we stood next to it, cheering, completely unaware of the ancient, silent hunters crouching in the trees who just noticed the light. The signal is already out there. It is already propagating at the speed of light in every direction, and it cannot be called back. Number 2. The universe could delete itself and you would never know. There is a scenario in theoretical physics where the universe destroys itself, not slowly through heat death or entropy. Instantly, time at the speed of light, a bubble of true vacuum nucleates somewhere in space, perhaps triggered by nothing more than a random quantum fluctuation, and begins expanding outward in every direction. Inside the bubble, the laws of physics are rewritten. The electromagnetic force changes strength. The strong nuclear force may vanish entirely. Atoms cannot form. Chemistry does not exist. Life is impossible. And here's the part that makes this different from every other cosmic threat. You cannot see it coming. The bubble expands at the speed of light. The very first photon announcing its existence is the bubble itself. By the time the light from its leading edge reaches your retina, you have already been erased. No warning, no observation, no last moment of awareness. You simply stop existing instantaneously without ever knowing it happened. Yet the concept emerges from quantum field theory and the nature of the Higgs field. The field confirmed at CERN in 2012 that gives particles their mass. Current measurements of the Higgs boson mass, approximately 125 giga-electron-volts combined with the top quark mass, place the Higgs field in what physicists call a metastable state. Stable enough to persist for billions of years, but not at its lowest possible energy. A sufficiently energetic quantum event could, in principle, kick the field into its true ground state, triggering a phase transition that would rewrite the fundamental constants of nature. The scientific consensus is that false vacuum decay, if possible, is extraordinarily unlikely on human timescales. The expected half-life of our metastable vacuum has been estimated at many orders of magnitude beyond the current age of the universe. We are almost certainly safe. But almost certainly is not definitely. And quantum mechanics is a game of probabilities. The same probabilistic framework that governs radioactive decay, random, unpredictable, fundamentally unschedulable, is the framework that governs vacuum transitions. Imagine living your entire life on a frozen lake. The ice is thick. It has held the weight of your family for generations. Every measurement confirms it is solid. But deep in its molecular structure, there is a phase transition waiting. A crack that could form at any point for no predictable reason, cascading outward at a speed no one can outrun. You have been told the ice is stable, and it is, right up until the moment it is not. False vacuum decay is the ultimate existential horror because it renders every other threat meaningless. Asteroids can be deflected. Supernovae can be survived if you are far enough away. Even gamma-ray bursts operate within the known laws of physics. Vacuum decay does not. It is the laws of physics turning against you. And the most chilling possibility, it could have already started. Somewhere in a distant corner of the observable universe, a bubble of true vacuum may already be racing toward us at the speed of light. We would not know. We cannot know. The information about its existence travels at the exact same speed as the destruction itself. Reality may already have an expiration date. And the clock is invisible. Number 1. The universe is suspiciously perfect, and nobody knows why this is number 1. And this is the one that breaks everything. There are at least 26 fundamental constants in physics. The gravitational constant, the speed of light, the mass of the electron, the strength of the strong nuclear force, the cosmological constant that governs the energy density of empty space. These numbers were not chosen by anyone. They were not designed by a committee. They simply are. And if you change any single one of them by even a fraction of a percent, the universe as we know it ceases to exist. The cosmological constant is fine-tuned to 1 part in 10 to the power of 120. That is a 1 followed by 120 zeros. If this value were slightly larger, the universe would have expanded so rapidly that no structures could ever form. No galaxies, no stars, no planets, no anything. Slightly smaller, and the universe would have collapsed back on itself billions of years ago. How a 2% change in the strength of the strong nuclear force would prevent hydrogen from fusing into helium. No stars, no energy, no periodic table. A 0.5% shift in the electromagnetic force would destabilize carbon atoms. No organic chemistry, no DNA, no life. Not unlikely, impossible. Roger Penrose, one of the most distinguished mathematical physicists alive, calculated the probability of the universe beginning in the specific low entropy state required for its current structure. The odds he arrived at, 1 in 10 to the power of 10 to the power of 123. That number is so incomprehensibly vast that if you wrote a single 0 on every atom in the observable universe, you would not have enough atoms to finish writing it. There are only 3 explanations, and none of them are comfortable. The first is pure coincidence. What the constants landed on the one configuration out of an effectively infinite number of possibilities that permits complexity, consciousness, and your existence. The odds against this are so extreme that calling it unlikely does not begin to describe the situation. The second is the multiverse. There are an effectively infinite number of universes, each with different constants. We exist in one where the constants work because we could not exist in one where they do not. This is the anthropic principle. It is logically valid. It is also untestable, unfalsifiable, and functionally indistinguishable from a creation myth dressed in the language of physics. The third is intentional design. The constants were set deliberately by something, for some purpose. This is the explanation that makes physicists the most deeply uncomfortable. Why? Because it crosses the border from empirical science into a territory that science was specifically constructed to avoid. And this is where every thread we have pulled tonight comes together. The expansion rate that does not match. The galaxies that should not exist. The 95% of reality we cannot see. The star older than the cosmos it inhabits. The void that should not be empty. The star that blinks for reasons we cannot name. The invisible hand pulling us beyond the edge of the observable universe. The silence of a galaxy that should be teeming with voices. The vacuum that could erase everything without warning. And now, the final discovery. The suspicion, grounded in mathematics, that none of this is accidental. We do not have the answer. After 4 centuries of physics, a century of cosmology, you do in the most powerful telescopes, particle accelerators, and computing systems ever conceived by any species on any world, the single most fundamental question remains unanswered. Why does the universe work? Not how. We are making extraordinary progress on how. But why? Why these constants? Why this configuration? Why anything at all? The honest answer, the one sitting quietly at the bottom of every equation, every observation, every Nobel lecture, is 3 words that should terrify you in their simplicity. We don't know. Sleep well. I'll be sharing more similar videos in the future, so subscribe to stay tuned.